Okay, last aspect that I want to do is body forces. How do we apply body forces? And that's really, I'm going to just remind you to go back to your textbook. You see the body forces. We need to do sort of this integral. Thickness, integral minus 1 minus 1, nt det j, and then fx, fy is the body forces in the x and y direction. Okay, so that's just to, as a reminder. So let's go back and see. So what it boils down to is the following. We need to just essentially compute nt, n transpose, that we already have done now multiple times. We have to put in the body force vector, fx and fy, then the thickness, the determinant of the Jacobian, and that's it. Okay, so dx dy is equal to the determinant of the Jacobian of d sine d eta, so this is where this comes from. The thickness makes it then this area, or this dA, which is then the area of volume, and then lastly, this is what we need to compute. So let's say consider constant body force of minus 20 Newton per millimeter cubed, okay, in the y direction over a square to an element of side length 10 millimeters and a thickness of 1 millimeter. So what I'm going to do is I'm going to do this now formally so that you can see nicely. So I'm going to take the x coordinates. So all I'm doing is I'm taking my x coordinates. This is my x, y for node 1, x, y for node 2, x, y for node 3, x, y for node 5, 6, 7, 8, 9, 10. Sorry, node x, y node 1, x, y node 2, x, node 3, x, y node 4, x, y node 5, x, y node 6, x, y node 7, x, y node 8. Okay, sure, I'm running away from my, yeah. Okay, so that's that. And so what I have got here, this n is a 16 by 2. So what I'm doing is, sorry, the n is a 2 by 16, and so what I'm doing is this 2 by 16 I multiply essentially by a 16 by 1, and I end up with x, which is a 2 by 1. That's really what I'll be ending up with after I've multiplied these two. So I'm not taking n transpose to make it a 16 by 2. I'm leaving it as a 2 by 16. 2 by 16 times 16 by 1. Now I've got a 2 by 1. That's my x and y coordinate. Then I can say take this, take essentially this vector, and take the derivative with respect to sine eta to get the Jacobian. Then I can say let's just convert this into a numerical system. So just using numpy array to convert it to a float. It was symbolic. As you'll see here, it's just constant values in here. That's why I can do that. And then I'm just reshaping and make sure it remains a 2 by 2 matrix. Compute the determinant of that. I'm just showing you what the determinant is. Okay. Then essentially, I apply the body force of 0 for x and minus 20 for y. Thickness of 1. I construct my integrand and then I just do numerical integration. So here I'm doing a 2 by 2 Gauss quadrature rule. So these values, sine eta minus a third, then plus a third minus a third, plus a third plus a third, minus a third plus a third. That's sort of the 4 Gauss points where I evaluate this integral to integrate it. Okay, so let's start off. If I run this, what I first want to show is the Jacobian that I'm printing. That's that value there. Then I'm printing the determinant, which is that value there, and then lastly I'm printing the load vector. Okay, and what I want to show you is the body forces are essentially in the y direction. So every second one will be a value. Every odd position, if I think of this as position 1, 3, 5, 7, will be zeros because there's nothing in the x, it's only in the y. So what I'm getting out is 166, 166, 166, 166. But remember, we applied in the negative 20 direction. So what you're seeing is this is going up, 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 up. These ones are minus, 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 minus. This is how the body forces distribute. So what we're seeing is essentially at the main nodes, we're getting these positive values, although we're applying a body force in the negative direction, and in the mid-side nodes, we're getting these large negative values. That's what we're seeing. Okay, so let's make sense of it, just to make sure that we agree with what we see here. So what I've shown here is just some notes from Professor Rafi Afka. Unfortunately, he passed away earlier this year from Florida University. But just to show you, because unfortunately the textbook that we have don't have an example of the body forces, what the distribution should look like. But this is just to show you uniform body force, work equivalent nodal forces corresponding to weight as a body force, rectangular quadrilaterals for work equivalents. And what it's showing here is that if I have a total load in terms of body force. If I take that body force that I've got here, so what it is this body force of 20, and I multiply it by the volume over which is the element's volume. That is what this W implies. Okay, so here I'm computing it. It's essentially 20, so I must make it just negative 20. So if I want to keep directionality, but what we're seeing here is essentially negative 20. This is the rectangular area, 10 by 10 times 1/5 thickness minus 2000. That's a total sort of weight load that I'm applying. Okay, if you want to think of it like that. Then there should be a 12. And this is showing you at the main nodes it's going up. Okay, in the mid-side nodes things are going down. So this is essentially exactly what we saw here. Okay, stuff going up, and then here stuff going down in the direction which we want to apply stuff. Okay, so what's important is we need to figure out, is this 112, 1/3, 112 true? So what I'm going to do is I'm going to say let's print the load. Okay, I'm going to divide by the 2000 newtons, which I've just calculated here at the top. So I'm just going to divide by that. So let's divide by the minus 2000 there, which was the. Let's just divide by the magnitude. I'm going to confuse the sign issue now. So I'm just going to divide by the magnitude of 2000. And what I should see then is essentially this kind of split of 112, 1/3, because this is a uniform body force. So if I do that, if I do that, what I'm getting out is this 0.0833, and just to show you what is the value for 112 and print what is the value for 1/3. You can already see 1/3 are spot on. Okay, so this is just to show you. Well, if I print out the value for 112, I'll get this value. So these are the values for 112, 112, 112, 112, and then 1/3 are these mid-side nodes that I'm getting out. And so all of this makes complete sense from a sanity check from what you expect to see from sort of any literature that you'd open up beyond the textbook that we've used in this course. Okay, this is how we apply body forces, as simple as this in a two-dimensional setting. So this is just to make sure that we can also then go about modeling that bar hanging its own weight, if you would like to give that a go using quadrilateral Q4, Q8 elements, depending on what you would like to do. Okay, so hopefully this gave you a good overview of consistent node loads, what it's all about, extending a little bit on what we've done on just in terms of traction, to say also now we've looked at it applying point loads between nodes, as well as essentially applying body forces. Thank you.